drifting silently through the space between Mars and Jupiter. An object from another star system has passed through our own. This interstellar visitor, known as 3I Atlas, carried within it a chemical composition that our current understanding of the universe says should not be possible. This isn't a theoretical anomaly. It is a measured fact, confirmed by two of the most sophisticated observatories ever constructed. The chemistry of 3I Atlas is so profoundly unusual that the only known natural process that could explain it would require a protoplanetary disk colder than the cosmic microwave background, the faint afterglow of the Big Bang itself. This scientific puzzle, however, was quietly transformed into a matter of planetary security in April of 2026, following a paper from Harvard astrophysicist Avi Loeb. His analysis brought a chilling possibility to light. Should an object like this ever be on a collision course with Earth, our standard defense protocol, the nuclear option developed by Edward Teller following the impact of Shoemaker-Levy 9, would be the very action that ensures our destruction. Detonating a nuclear device to shatter it would not protect our world. Instead, it would ignite a fuse, unleashing a 1-0 teraton chain reaction, equivalent to 200,000 Tsar bombers, that would vaporize the object in 1/100th of a second. As we explore this further, a counterintuitive truth may emerge. In the face of such a threat, inaction might be our only path to survival. If this revelation sparks your curiosity, we invite you to continue the journey with us here on Calm Space. The story of 3I Atlas is far from over. Although the object itself is now departing our solar system, the profound questions it has raised remain. Its passage has forced us to confront new possibilities about the universe and our place within it. As new data continues to arrive from observatories around the world, we will be here to carefully interpret what it all signifies. The discoveries ahead promise to be just as compelling. It all begins with a measurement that nobody expected to see. Within a peer-reviewed scientific paper lies a number so anomalous it seems to defy existence. This is not the result of a simple typo, a calibration error, or a single instrument malfunctioning. The finding was independently verified by two separate observatories located on different continents, each examining different molecules using distinct parts of the electromagnetic spectrum. Yet, despite their different methods, both facilities returned the same, seemingly impossible result. The object of their study was 3I Atlas, and the discovery of its composition has fundamentally altered our perception of what interstellar space can send our way. The raw measurement itself tells the entire story, so let us examine it closely. From its vantage point 1.5 million kilometers from Earth, the James Webb Space Telescope detected the infrared signature of water vapor sublimating from the object's surface. Simultaneously, the Atacama Large Millimeter, Submillimeter Array, a network of 66 radio dishes high in the Chilean Andes, observed the millimeter wave signature of methane gas. Both teams performed the same kind of detailed chemical forensics. They analyzed how much of the hydrogen in these molecules was actually deuterium, a heavy isotope of hydrogen containing an extra neutron. The results were startling. The water on 3I Atlas showed a deuterium to hydrogen ratio of approximately 0.95%, while the methane exhibited an even more extreme ratio of 3.31%. To understand the significance of these figures, we must compare them to the cosmic standard. Across the universe, the average ratio set by the Big Bang is about 1 deuterium atom for every 40,000 atoms of normal hydrogen. This is the baseline we find in interstellar gas and the general chemistry of our galaxy. Yet, the methane on 3I Atlas contains a ratio closer to 1 deuterium atom for every 30 hydrogen atoms. This represents an enrichment more than 1,000 times higher than the galactic average, a deviation of 3 orders of magnitude. Such a dramatic departure from the norm is a powerful indicator that a truly unusual process shaped this object's formation. It's a moment that demands our attention. Two independent teams, using different instruments to study different molecules, both concluded that the hydrogen on this object is profoundly abnormal. When two distinct lines of evidence converge on such a wild, almost unbelievable enrichment, the finding can no longer be dismissed as an anomaly or instrumental noise. It must be accepted as data, and this data tells an extraordinary story. The measurement from the methane is particularly revealing, even more so than the water. The chemistry of deuterium acts as a kind of cosmic thermometer. In extremely cold environments, and over many chemical reactions, deuterium has a tendency to concentrate preferentially in some molecules. Methane is one such molecule, readily incorporating heavy hydrogen under these frigid conditions. Therefore, discovering methane with such a high level of enrichment means we are observing an object whose chemistry was forged in an environment of almost unimaginable cold, where it absorbed deuterium like a sponge. While water also becomes enriched, the process is slower and less pronounced. Methane, in this context, serves as our most sensitive probe, and its readings are pointing to something truly exceptional. The entire conversation surrounding 3I Atlas shifted in April of 2026 with the publication of a paper by Harvard's Avi Loeb. Until that point, scientific discourse had centered on its origins, questions about the star system that produced it, its journey through interstellar space, and what its path might reveal about our stellar neighborhood. These were all valid and important scientific inquiries, but as it turned out, they were not the most urgent. Loeb approached the problem from a different angle. He shifted the focus from where the object came from to what the object was capable of. The calculations he performed are the central reason for this discussion, as they revealed a potential far more immediate and concerning than its mysterious past. Loeb's analysis began with the object's minimum estimated mass, a staggering 160 billion kilograms, or 1.6 x 10^11 kilograms. He then considered this mass in light of its unique chemical makeup, where a significant portion of its hydrogen is deuterium. When subjected to immense pressure and heat, deuterium nuclei fuse together, releasing enormous amounts of energy. This isn't theoretical or exotic science. It is the very same nuclear fusion process that powers our sun and that humanity has sought to replicate in fusion reactors for over 70 years. At a sufficient scale and density, this process can trigger a runaway chain reaction. This realization represents a fundamental shift in our understanding. Until now, every interstellar object we have observed has been inert comets and asteroids composed of rock and ice that pose a threat only through their kinetic energy. They are dead objects. 3I Atlas is different. It carries its own immense store of releasable energy. As Loeb's analysis bluntly suggests, its composition makes it, in effect, detonable. Consider a reservoir of fuel, a deposit of what appears to be fusion-grade material drifting through our solar system at tens of kilometers per second. The only thing standing between that fuel and a catastrophic energy release is the absence of a trigger. This single fact makes the years of debate over its path seem secondary. We have questioned its trajectory, but an object's composition is more revealing. A strange path suggests something pushed it. A strange composition tells you what it is. And according to the data, this object is something we cannot explain with natural models and something our planetary defense plans never accounted for. It is important to be precise here and avoid hyperbole. No one is saying the object 3I Atlas will strike Earth. It won't. It is already heading away from us. Nor is anyone stating it is definitively artificial. The research makes no such claim. The actual assertion is far more uncomfortable. What is being said is that we have detected a class of object whose existence implies some bodies drifting between stars are not passive. They are loaded. Our standard procedures for incoming threats were written assuming nothing out there is loaded. That foundational assumption is now in jeopardy. The unease in the scientific community is real, even if unspoken. You can feel it in the cautious hedging of papers and in how discussion has shifted from observing an interesting object to questioning what to do if we find another. That is the real question. 3I. Atlas is leaving, the window for direct study now closed. But it is not the last interstellar visitor. It is just the third we have ever seen. And if 1 out of 3 has this property, the unseen population we have not yet detected is a profound source of concern. This is not about what 3I Atlas is. It is about what it can do, and what its cousins might do, and what we would do if we ever saw one heading for us. According to researcher Avi Loeb, the obvious response is the worst possible one. The Edward Teller playbook, our assumed last resort for a large impactor, gets inverted by a body like this. Drop a nuke on a normal asteroid, and you fragment it. Drop one on 3I Atlas, and you don't fragment it, you light it. The chilling question is whether we would even know the difference in time to choose correctly. So our story begins with an unexpected measurement, a challenging analysis, and a new category of object no one had anticipated. As we continue, we will explore what sets this visitor apart from the two that preceded it. We will examine why those distinctions are critical, and how its internal chemistry seems to defy the known laws of cosmic formation. In the entire history of astronomy, only 3 confirmed interstellar objects have passed through our solar system, just 3. This tiny sample size means any conclusions must be treated with extreme caution. To understand the significance of this third visitor, it is essential to look at all 3 in sequence, as the contrast between them tells the real story. The first was 1I, Oumuamua, spotted in 2017. It made headlines because it accelerated as it moved away from the sun, a change in speed that could not be explained by gravity alone. Comets sometimes exhibit this behavior when ice on their surface boils away, creating tiny jets that push the object. But Oumuamua had no visible coma. It wasn't venting any material we could detect. The unexplained acceleration led to a host of theories, from exotic ices that vaporize without leaving a dusty trail, to a fragment of a distant Pluto-like world, to the more controversial hypothesis from Avi Loeb that it might be a thin, engineered structure pushed by solar radiation. That debate continues, but the key point is what kind of anomaly it was, a mystery of motion. The object was simply moving in a way it shouldn't. The second visitor, 2I, Borisov, arrived in 2019. In the most reassuring way possible, Borisov was wonderfully boring. It was, quite simply, a comet. It looked like a comet, it outgassed like a comet, and its chemical makeup was broadly what one would expect from a comet that had formed around another star. While there were some minor differences in the abundance of certain ices, nothing about it broke our existing models. Borisov served as the perfect control sample, confirming that yes, comets do exist around other stars, and they look remarkably similar to our own. It was a moment of scientific relief. And then came 3I, Atlas. This object presented a puzzle of an entirely different order. Here, the primary anomaly was not found in its motion. It was not even centered on its outgassing pattern, although that too had its peculiarities. The core mystery lies in its very substance, the fundamental atomic ratios of its material. This represents a chemical anomaly, a type of discrepancy that is far more difficult to explain away than an unusual trajectory. Across these 3 objects, a distinct pattern begins to emerge. We progressed from a dynamics anomaly with Oumuamua, which could have various physical explanations, to the baseline normality of 2I, Borisov. Now, with 3I, Atlas, we face an anomaly of composition. This progression is significant because an object's motion can be influenced by many external factors, a hidden jet, a gravitational nudge, or even a measurement error. but its composition is its intrinsic nature. You cannot easily alter what something times is. You can only seek to explain it, or, as in this case, find that our current models fall short. We are therefore looking at a pattern where the mystery is not just continuing, but deepening with each new visitor. A concept quietly emerging in scientific literature, which helps frame this mystery, is known as pattern stacking. The idea is simple. A single, weak anomaly can be dismissed. Two might be a coincidence. But when 3 or 4 unusual traits are stacked together on the same object, their combined signal can no longer be dismissed as mere noise. 3I, Atlas exhibits just such a pattern. It displayed unusual outgassing. Its deuterium chemistry is deeply strange. And its trajectory contains features that researchers have flagged as requiring a closer look. While each of these could be explained away in isolation, their convergence on a single object creates a compelling and unsettling picture. This statistical discomfort is difficult to ignore. If one of the first 3 interstellar objects we have ever observed possesses chemistry that our models suggest should not exist, we are left with a few startling possibilities. Perhaps we have been astronomically fortunate to witness such a profound outlier so early in our search. Or, these objects are far more prevalent than we ever imagined. Or, most unsettling of all, our fundamental models of what is normal in the cosmos are simply wrong. None of these options is comfortable, and they all lead to a single, sobering conclusion. The study of interstellar objects has transformed from a curiosity of observational astronomy into a problem of risk classification. We are no longer just cataloging visitors from afar. We are now trying to determine which ones might be dangerous, and in ways we have not yet learned to categorize. At the heart of this reevaluation is the chemistry of deuterium, for it is here that the true nature of the risk resides. To understand this, we must first explore the problem of deuterium itself. In simple terms, deuterium is hydrogen with a passenger. Whereas a normal hydrogen atom's nucleus contains a single proton, a deuterium atom has both a proton and a neutron. This extra neutron, though small, changes everything about the atom's behavior. It is heavier, so it moves more slowly. It forms stronger bonds in chemical reactions, and most crucially, it can fuse. When 2 deuterium nuclei are slammed together with enough force, they undergo nuclear fusion, releasing a tremendous amount of energy. This single fact is essential to understanding everything that follows. There is a fundamental rule about deuterium that governs this entire story. Stars are destroyers of deuterium. The immense temperatures and pressures inside a star's core are more than sufficient to fuse deuterium with extreme speed. This means any deuterium that finds its way into a star is consumed almost immediately. Consequently, the universe has been steadily losing its deuterium since the first stars ignited billions of years ago. Any deuterium that exists today is either a primordial remnant from the Big Bang itself, or it has been carefully preserved in cold, dark environments that have never been processed through the furnace of a star. This reality creates a natural ladder of deuterium abundance, and it is this ladder that makes the case of 3I, Atlas, so profoundly disturbing. At the very top of this ladder is the Big Bang, which produced a primordial deuterium to hydrogen ratio of roughly 1 in 40,000. This is the universal baseline. Below that, in the interstellar medium, the thin gas drifting between the stars, the ratio is similar, though it can be slightly enhanced in cold, dense regions. Descending further, we reach the solar nebula, the disk of gas and dust that formed our own solar system. Here, chemical processes nudged the ratio up slightly, to the order of 1 or 2 in 10,000. Next are comets, which are essentially frozen samples of that primordial nebula, preserved for 4.5 billion years. In comets, deuterium ratios can range from 1 in 10,000 to a few in 10,000, representing the most deuterium-rich material in our natural solar system. Just below that, in Earth's oceans, the ratio is about 1.5 in 10,000, a number that strongly suggests our planet's water was delivered by comet-like bodies long ago. And then, far below all of these, in a category entirely its own, sits 3I, Atlas. The water ice on this object is nearly 1% deuterium, and its methane is over 3%. To climb from the cosmic baseline to the measurements taken from 3I, Atlas, you would need to enrich the deuterium content by a factor of roughly 1,000. This is not a minor adjustment. It represents a complete and total rewriting of the known rules of chemistry. To give this context, consider the Rosetta mission, which orbited comet 67P Churyumov-Gerasimenko between 2014 and 2016. It provided our gold standard measurement for cometary deuterium, finding a ratio about 3 times that of Earth's oceans. At the time, that was considered surprisingly high and pushed the boundaries of what natural cometary chemistry was thought to produce. 3I. Atlas is approximately 100 times more enriched than that record-setting comet. We are not in the same regime. We are not looking at the same chart. We are far off the edge of the map entirely. The puzzle deepens because the water and methane on 3I, Atlas, are not enriched by the same amount, which is itself a powerful clue. The water shows a deuterium level of about 0.95%, while the methane is at 3.31%. This means the methane is more enriched than the water by a factor of roughly 3.5. Chemists call this phenomenon differential fractionation, and it tells you something very specific about the object's origin. Whatever process enriched this material had to be operating at extraordinarily low temperatures. How cold must this environment have been? We are talking about temperatures down in the range of 10 Kelvin and possibly even lower. 10 Kelvin is just 10 degrees above absolute zero. It is colder than the surface of Pluto, colder than a comet hibernating in the dark outer reaches of the Kuiper belt. It is a degree of cold for which we have almost no precedent in natural planet-forming disks. And it is here that we run into a fundamental wall. The universe itself has a temperature floor set by the cosmic microwave background, the faint leftover radiation from the Big Bang. That floor is about 2.7 Kelvin today. This means the environment that produced the chemistry of 3I, Atlas, must have been colder than 10 Kelvin, but warmer than 2.7 Kelvin. While such a temperature window is possible in principle, maintaining it in a place that also contains enough methane and water for enough time to run this extreme chemistry is extraordinarily difficult to imagine. Our models can account for some of this. We know of dense pockets of gas in molecular clouds, called prestellar cores, where iron molecule chemistry can unfold at very low temperatures over long periods, enriching deuterium beyond the baseline. We have even detected molecules like multiply deuterated formaldehyde in these regions, so we know the basic chemistry works. What we have never seen, however, is this process operating on a bulk scale, not in kilograms or gigatons, let alone the 100 billion kilogram scale of an entire interstellar object. The localized chemistry happens, but the wholesale chemistry needed to build an entire body from this enriched ice has never been observed and is not predicted by current models without invoking significant new physics. This is the core of the tension, a choice between statistical rarity and what appears to be a chemical impossibility. Statistical rarity suggests an event is improbable, yet conceivable, while chemical impossibility implies a violation of the fundamental laws of nature as we know them. The object known as 3I Atlas occupies a curious space somewhere between these two definitions. Where it truly belongs on that spectrum depends entirely on which scientific models one finds most credible and how far one is willing to extrapolate their findings. There is another context where deuterium is deliberately enriched to such high levels, a parallel that has become an unavoidable part of this conversation. Here on Earth, we purposefully create this condition in laboratories to produce fusion fuel. Every fusion experiment on the planet, from tokamaks to inertial confinement systems and even proposed fusion propulsion designs, relies on enriched deuterium, often mixed with tritium to enhance the reaction's yield. While the enrichment levels in our labs are typically higher than what was measured on 3I Atlas, the underlying principle remains identical. To make a substance fuse with maximum efficiency, you load it with deuterium. From the viewpoint of a fusion engineer, this means 3I Atlas is, quite literally, fuel. Its composition falls within the range that would be loaded into a fusion reactor. This is not an assertion of artificial engineering, but a statement that whatever process formed it natural or otherwise created a substance chemically indistinguishable from what we ourselves would design for rapid interstellar flight. If the object is indeed fuel, then the next logical question must be one of ignition. After all, fuel on its own is passive. It only becomes a hazard when something provides a spark. Nature, it seems, can produce extreme deuterium enrichment, but only just barely, under theoretical conditions we are not even certain exist outside of our models. By contrast, engineering would produce such enrichment deliberately, as that is the entire purpose of the process. The measurement from 3I Atlas lies precisely on the line separating these two explanations. Yet the consequence, regardless of which side of that line one favors, is the same. A reservoir of fuel is cruising through our solar system. This discovery presents a new imperative, forcing us to ask a question we have never had to consider before. What could set it alight? Much of the discourse surrounding 3I Atlas, prior to a pivotal paper by Loeb in April, had centered on passive observation. What could we see? What could we measure? What might we deduce about its origins? Loeb's contribution was transformative because it shifted the focus of the entire conversation from observation to intervention. The paper posed a new and unsettling question. What happens if some entity, human or otherwise, decides to act upon this object? At its core, the work is an analysis of consequences, and it identifies one that had, until that point, been completely absent from the discussion. The critical line that had been missed is this. If you apply our standard planetary defense procedure to a hazardous body like 3I Atlas, you will not simply break it apart, you will ignite it. The very technology we have been quietly developing as our last resort against a major impact, a nuclear standoff, or subsurface detonation, becomes the instrument that transforms a kinetic threat into a thermonuclear one. The most unsettling part is that the underlying physics has been understood for nearly a century. We just never imagined a scenario where it would apply to a comet. Let us journey back to the year 1942, during the height of the Manhattan Project. For a brief but significant moment, some physicists on the project harbored a deep concern that a fission detonation could ignite Earth's entire atmosphere. Their reasoning was that nitrogen nuclei in the air might fuse under the intense conditions of a nuclear blast, setting off a propagating chain reaction that would circle the globe. Hans Bethe, the brilliant theorist who would later earn a Nobel Prize for his work on how stars generate energy, was tasked with performing the calculations. He meticulously worked through the densities, the reaction cross-sections, and the rates of energy loss through radiation. His conclusion was definitive. The atmosphere is far too diffuse for a fusion chain reaction to sustain itself. Any energy released by localized fusion would radiate away more quickly than it could heat the adjacent layer of nitrogen to ignition temperatures. The sky, he proved, is safe. That conclusion, while rock solid for our planet, is entirely irrelevant when considering 3I Atlas. This is because 3I Atlas is nothing like the atmosphere. Where our atmosphere is thin and wispy, 3I Atlas is solid, dense, and opaque, all while being packed with deuterium. The very conditions that Hans Bethe determined would prevent a chain reaction in the air are precisely the conditions that exist inside this object. Therefore, one cannot simply rely on the standard reassurance that fusion reactions do not chain in nature. Within 3I Atlas, the geometry is different, the opacity is different, and the fuel concentration is different. Every single parameter that guarantees the safety of our sky is reversed inside this interstellar visitor. This realization introduces what can be thought of as a new classification of celestial body, the reactive object. For our entire history of contemplating asteroid and comet defense, we have operated under the implicit assumption that these bodies are inert. We believed that when you push them or strike them, all you get in return is kinetic energy and scattered rubble. That fundamental assumption is now broken. 3I Atlas demonstrates that some objects in the cosmos are not inert at all. Instead, they are stable but loaded. They are stable in the sense that they will not spontaneously detonate, but loaded in that they contain enough fusible material for the right kind of disturbance to trigger a runaway energy release. This represents a new category of potential hazard we had never before conceived. This brings us to the concept of a trigger threshold, which is worth examining closely. As 3I Atlas drifts through the cold vacuum of space, it is not going to spontaneously do anything. The deuterium locked within its structure is not unstable or radioactive. It could remain there for billions of years, behaving just like any other piece of ice. The danger is not in what the object does on its own. The danger lies in what might happen if it is disturbed with sufficient energy. By disturb, we mean an event that would momentarily create the extreme temperatures and pressures needed to initiate fusion. A fission bomb detonated near or inside it could certainly do this. So too could certain high-speed impact scenarios, depending on the geometry of the collision. And once a reaction starts within a body this dense and opaque, it does not necessarily have to stop. It has the potential to propagate. To make this clearer, it is useful to draw an analogy. Think of 3I Atlas as a fuel tank, a truly colossal one. The fuel it contains is stable at its ambient temperature, which in this case is the near absolute zero of deep space. You can fly this tank around. You can even throw it, and it remains a passive, frozen mass. But the moment a sufficient spark is introduced, the fundamental nature of the object is transformed. It ceases to be an inert rock and becomes an active, energetic event. Consider an object like a simple tank of fuel. A gentle tap will produce no effect. It remains inert. But if a spark of sufficient intensity is introduced in just the right location, the entire reservoir can erupt. This is not some exotic characteristic, but the fundamental nature of stored chemical energy. The truly extraordinary aspect of the object, known as 3I Atlas, is its sheer scale. The fuel it contains is estimated in the tens of billions of kilograms, and the energy locked within its molecular bonds is measured on a scale we rarely encounter outside of theoretical astrophysics. This brings us to the trigger problem, which transforms this from a passive astronomical curiosity into a serious matter of planetary defense. If 3I Atlas were on a collision course with Earth, which, to be clear, it is not, and we took no action, the impact would be a terrible, but ultimately localized, kinetic event. Its destructive power would be bounded. However, if we were to strike it with a nuclear device in an attempt to break it apart, the outcome would be qualitatively different and orders of magnitude worse. This is because such an impact would not merely fracture the object, it would act as a catalyst for its deuterium fuel. Edward Teller, a key architect of the hydrogen bomb, was intimately familiar with this physics. He simply never conceived that we might one day find a target composed of raw fusion fuel hurtling toward us from interstellar space. This realization places us in a strange and precarious new position. For the first time, we have identified a class of object where the very act of defending against it could be far more dangerous than simply letting it pass. It presents a profound and unsettling paradox where the safest response, counterintuitively, might be to do nothing at all. Our entire understanding of this new object class is built upon a single example, 3I Atlas, which is now departing our solar system forever. We will not have the chance to study it at close range or analyze a sample of its material. Instead, the risk models we are now forced to consider are based on what amounts to 3 nights of telescope observations and a handful of independent spectroscopic measurements. This fragile foundation of data suggests we may have just discovered something we cannot safely interact with. The most disturbing part of this revelation is not our inability to touch this specific object, as 3I Atlas is already on its way out. The true anxiety stems from the precedent it sets. We must now operate under the assumption that the next interstellar visitor we detect could possess these same properties. And crucially, we currently have no way to determine from a distance whether it does or not, at least not in time to make the right decision. This is the intractable problem we now face. To fully grasp the nature of this threat, we must descend into the physics of how such an ignition would actually begin and propagate. This brings us to the chain reaction that no one had ever planned for. When 2 deuterium nuclei approach one another with extreme proximity on the order of 1/10 trillionth of a meter, the strong nuclear force overwhelms the electrical repulsion between their positive charges, causing them to fuse. This fusion event can result in one of 2 outcomes, each with a roughly equal probability. The first path yields a helium-3 nucleus and a free neutron. The second produces a tritium nucleus and a free proton. Both of these pathways release a tremendous amount of energy, between 3 and 4 million electron volts for every single reaction. This energy is expressed as the kinetic motion of the resulting particles, sending the new neutrons and protons flying outward at high speed. This initial reaction is just the first step, but it sets the stage for something far more powerful. Once a population of deuterium nuclei begins to react, it starts to generate tritium as a byproduct. This is the critical next step in the sequence. Tritium, an even heavier isotope of hydrogen containing 1 proton and 2 neutrons, fuses with deuterium far more readily than deuterium does with itself. This deuterium-tritium reaction has a much higher cross-section, meaning it is statistically more likely to occur. And it releases significantly more energy, approximately 17 million electron volts per event. The vast majority of this energy is carried away by a single, high-speed neutron that blasts through the surrounding material. What emerges from this is a powerful feedback loop. Deuterium fuses with deuterium, producing tritium. That tritium then fuses with more deuterium, generating extremely energetic neutrons. These neutrons, in turn, travel through the object and can deposit enough energy into other deuterium nuclei to spark new fusion reactions. This cascading process is the very definition of a chain reaction, built upon the same fundamental architecture as a hydrogen bomb. The foundational insight, attributed to Edward Teller and Stanislaw Ulam in 1951, was that a primary fission explosion could be used to compress and heat a package of deuterium fuel to the point where this chain reaction would ignite on its own. Once ignited, the reaction propagates, consuming the available fuel until the material is no longer dense or hot enough to sustain it. For any fusion reaction to become self-sustaining, a delicate balance of 3 critical factors must be achieved: density, temperature, and confinement. You need sufficient density for the fuel particles to find each other. You need a high enough temperature for the nuclei to move fast enough to overcome their mutual electrical repulsion. And you need confinement to hold the reaction together long enough for its energy production to exceed its energy loss. In a hydrogen bomb, these 3 conditions are met by using a fission primary to inertially compress the fusion fuel in a matter of microseconds. Within a star, they are achieved through the immense, unrelenting gravitational pressure of the star's own mass. In a tokamak fusion reactor, they are managed with powerful magnetic fields and precise external heating. The pivotal question for 3I, Atlas, is whether these same conditions could be met by an external trigger acting upon the object's natural state. The analysis by Loeb and his colleagues suggests the answer is yes, and their reasoning is grounded in standard fusion physics. The sheer bulk mass of 3I, Atlas, provides its own confinement. The object's inertia is so great that any internal event cannot expand and cool fast enough to extinguish itself. Its unique composition provides the necessary density, with deuterium concentrated to a point where reaction rates are high. All that is missing is the initial spark. An efficient trigger, detonated near the object's core, could provide the initial temperature and the necessary flux of neutrons to begin the cascade, which would then build upon itself until the entire enriched volume becomes a single, propagating thermonuclear front. Perhaps the most fitting analogy for this event is what physicists call a detonation wave. This is a self-sustaining front of reaction that moves through a fuel source at supersonic speeds. In conventional chemical explosives, this wave is driven by the release of chemical energy. In a thermonuclear context, however, it is propelled by the release of nuclear energy, with high-speed neutron carrying the ignition forward into unreacted fuel. This wave continues its relentless advance until the fuel is either completely consumed or the medium becomes too thin and diffuse to sustain the reaction. Imagining such a wave propagating through a body measured in billions of kilograms brings the scale of this potential hazard into stark relief. For a body the size of 3I Atlas, with the deuterium concentrations measured by the Webb telescope and ALMA, the fusion wave does not simply run out of fuel. Instead, the reaction continues until it runs out of the object itself. A sensible question immediately arises. Surely not every deuterium-rich object is a cosmic bomb waiting to detonate. And that intuition is correct. The vast majority of deuterium in the universe exists peacefully. As nature rarely provides the necessary trigger for ignition, the gravitational compression within a comet is far too weak, and the ambient temperatures of interstellar space are far too low. Even a direct impact from a smaller rock deposits its energy too superficially into too small a volume to initiate the chain reaction. This process has a threshold, and natural events almost never manage to cross it. A weak or even moderate impact on an object like 3I, Atlas would accomplish very little. A nuclear device, however, is engineered for the sole purpose of delivering the precise kind of energy density needed to surpass that threshold. This is where the story comes full circle, connecting a distant object to our own capabilities here on Earth. The significance of 3I, Atlas, the importance of these measurements, and the reason Loeb's paper commands attention is that our planetary defense toolkit contains an instrument designed to deliver exactly this kind of energy. That tool is the nuclear option. Until now, every object against which this option has been modeled has been chemically inert, incapable of responding in this way. 3I. Atlas is the first object in the recorded history of our solar system that, on paper, would not just fragment, but detonate. The physics suggests that ignition is plausible, not a certainty, but plausible enough to be the responsible default assumption when considering matters of civilizational risk. But before accepting this conclusion, we must address the standard objection, the one any physicist would raise. The argument that the energy will simply radiate away before it can build. This has been the reassuring counterpoint for years, and it is this objection we must now examine. Why does the radiative cooling argument fail in this case? The initial intuition seems perfectly reasonable. If you ignite a fusion reaction in a small, cold body floating in space, the heat should simply radiate out into the vacuum, causing the reaction to fizzle. After all, while a vacuum is a perfect insulator, space is also a perfect heat sink. Anything that gets hot will eventually cool. The standard thinking, therefore, suggests that any localized fusion within 3I, Atlas would radiate its energy away faster than the reaction could propagate, killing the chain reaction before it truly begins. This intuition, however, turns out to be wrong. The reason for its failure is a matter of simple geometry. In a fusion reaction, energy is generated throughout the entire volume of the reacting material, but energy is lost to radiation only from its surface. This distinction is critical because the volume of a sphere scales with the cube of its radius, while its surface area scales only with the square. As an object grows larger, this ratio becomes increasingly lopsided, heavily favoring energy generation over energy loss. In a tiny laboratory fusion experiment, where a fuel pellet might be a millimeter across, surface losses are dominant, requiring extreme compression and confinement to achieve net energy gain. But in an object the size of 3I, Atlas, hundreds of meters in diameter, the surface losses become almost completely irrelevant compared to the immense energy being produced within its volume. The body effectively insulates itself with its own bulk. Beyond geometry, the other half of the cooling argument is undone by the principle of opacity. As the interior of 3I, Atlas begins to heat up, the initial energy is released as radiation photons of various wavelengths. Yet these photons cannot simply fly out into space. They must first travel through the rest of the object, which is composed of dense, opaque material. This material absorbs and re-radiates the photons over and over again, forcing them on a slow, random walk toward the surface. The average distance a photon can travel before being absorbed, its mean free path, is incredibly short. Consequently, the time it takes for energy to diffuse from the center to the surface is very long. This creates a profound timescale mismatch. The fusion reaction seeks to release its energy in a fraction of a second, while the cooling process would need hours or even days to dissipate it. The reaction front, propagating through the fuel at a significant fraction of the speed of light, wins this race by many orders of magnitude, leaving the cooling process far behind. By the time any meaningful amount of energy has escaped as light or heat, the reaction is long over, and the object is nothing more than a rapidly expanding plume of plasma. The physicists of the Manhattan Project performed this same calculation in reverse when they considered whether a fission bomb could ignite Earth's atmosphere. They concluded, correctly, that the atmosphere could not sustain such a runaway reaction. The reason was that the atmosphere is so diffuse. Any localized fusion energy would radiate away into the surrounding colder layers long before it could trigger the next reaction. The medium is simply too thin to confine its own energy. 3I. Atlas presents the inverse scenario. The medium is so dense, so opaque, and so massive that any local fusion energy is trapped precisely where it is generated. It remains there, accumulating, until it builds enough pressure to drive the reaction front forward into the next layer of fuel. A useful way to visualize this process is to imagine a thermos flask filled with a liquid that is being heated from within. The heat cannot escape through the insulated walls fast enough to prevent the liquid from reaching its boiling point. Inevitably, the liquid boils. In the case of 3I, Atlas, the boiling is nuclear fusion, the liquid is the deuterium-rich ice, and the insulation is the massive body of the object itself. Critically, the shell is also the fuel. There is no separation between the heater and the material being heated. There is simply nowhere for the energy to go except into igniting more fuel. To anchor this concept in hard numbers, we can consider the object's sound crossing time. This is roughly how long it takes for a pressure wave to travel from one side of the object to the other. For an object with the size and density of 3I, Atlas, this timescale is on the order of 1/100th of a second, or about 10 milliseconds. This is the fundamental timescale on which the object can mechanically respond to changes in internal pressure. It is also, fatefully, about the same amount of time a detonation front would take to cross it. This means that by the time the surface of the object even knows the interior is detonating, the interior has already finished. The object does not have time to simply break apart. The reaction is too fast, consuming it from the inside out before it can respond. Once a process like ignition is considered possible, and once it is accepted that cooling cannot halt the ensuing chain reaction, we are compelled to confront the total energy that would be unleashed. This is the point where theoretical calculations manifest into a staggering physical reality. We now enter the domain of the 1-0 teraton reality. Let me present the figure first, and then we can explore its implications. According to Lowe's calculations, the total energy released in a worst-case ignition of 3-2 Atlas, based on its minimum mass and the measured deuterium concentrations, is roughly equivalent to 10 teratons of TNT. This translates to 10 trillion tons of TNT. In scientific terms, that is approximately 4x10, 22 joules, a colossal 40,000 billion joules of energy, all discharged in about 1/100th of a second. Such immense figures are difficult to contextualize, so let us turn to some comparisons. The most powerful nuclear weapon ever detonated by humanity was the Soviet Tsar bomber, tested in 1961, which yielded about 50 megatons. A megaton is 1,000,000 tons of TNT, whereas a teraton is 1,000,000,000,000. Therefore, 10 teratons is the equivalent of 200,000 Tsar bombers detonating simultaneously, a comparison Lowe himself makes. It is a vision of 200,000 of the largest weapons our species has ever built, all firing at the same moment in the same place. We can also consider the asteroid impact that caused the extinction of the dinosaurs 66 million years ago. The Chicxulub impactor is estimated to have released between 10 and 100 teratons of energy when it struck the Yucatan. This places the worst-case detonation of 3-2 Atlas in the same order of magnitude as the dinosaur killer. This comparison, however, is misleading without understanding the critical difference in how that energy would be delivered. The Chicxulub event was a kinetic impact, where most of the energy manifested as shock waves moving through rock and atmosphere, along with thermal radiation from the plume of ejected material. A thermonuclear detonation of 3-2 Atlas, by contrast, would release its energy as pure radiation. It would be an instantaneous and omnidirectional burst of light, neutrons, gamma rays, and high-speed plasma. The nature of the catastrophe would be fundamentally different. The damage profile from a pure energy release is profoundly distinct from an impact event. An impact concentrates its energy in one location, which then propagates outward via ground shock and atmospheric blasts. A detonation in space, however, would disperse its energy as electromagnetic radiation that travels at the speed of light, arriving at every part of a planet that is in its line of sight. If an object like 3-2 Atlas were to detonate within a few million kilometers of Earth, the consequences would be dire. The thermal pulse alone would be sufficient to set the entire dayside of our planet on fire. The accompanying neutron flux would be enough to activate the atmosphere, creating radioactive isotopes that would rain down for years. For a brief, terrible moment, the optical flash would be brighter than the sun, appearing as a blinding white point that would transform the sky into something the human eye was never meant to witness. At this scale, our standard nuclear blast scaling laws, the very equations used to estimate the effects of weapons tests, begin to break down. Those formulas were derived for yields ranging from kilotons to tens of megatons. Extrapolating them upward by 6 or 7 orders of magnitude is not a clean mathematical exercise. Nevertheless, the broad strokes remain. A 1-0 teraton detonation occurring within the atmosphere would have a blast radius measured in thousands of kilometers. The devastation would be on a continental scale, not regional or national. It would mean multiple countries flattened, with casualties in the millions from the immediate effects alone, and likely orders of magnitude more from the secondary effects of firestorms, climate disruption, and radiation. In the vacuum of space, far from Earth, a detonation would lack an atmosphere to drive blast waves, so the kinetic effects would be lessened. The radiative effects, however, would be arguably worse, as the energy would not be absorbed by air and would simply continue to travel. A 1-0 teraton detonation at a distance of, say, 1/10 of an astronomical unit, 15 million kilometers from Earth, would still strike our planet with enough thermal radiation to cause widespread fires on the dayside. At 1 astronomical unit, the radiation would be intense, but the immediate effects more limited. The unavoidable point is that there is no comfortable distance at which a body like this could detonate without consequence, should Earth happen to be on the wrong side of the geometry. Let me be unequivocally clear about one thing, as I do not wish to oversell the immediate threat. 3. Atlas itself is not going to detonate. There is no known mechanism by which it could. It is on a trajectory, leaving the solar system, and will not be struck by a fission device or anything else that might trigger ignition. The object I am describing is, for all practical purposes, harmless to Earth on its current path. The threat is not 3-2 Atlas. The threat is the next one. It is the population of similar objects that presumably exist in interstellar space. In numbers we cannot yet estimate, which may share the same chemistry. The danger is that one of those objects might eventually be on a different trajectory. Our response to that one will determine whether we still have a civilization the day after. This is where we must transition from understanding the energy yield to understanding what happens when that yield is triggered by us in a future scenario. Herein lies the true horror of Lowe's paper. It is not in the existence of 3-2 Atlas, which is a fascinating anomaly, but in the implication that our standard playbook for handling incoming threats, a playbook we have quietly trusted since the 1990s, is the very trigger for this kind of catastrophe. That this playbook was written by some of the same physicists who designed the first hydrogen bomb is a recursive fact that is difficult to reconcile. This brings us to Part 8, the Teller Playbook. The modern conversation about planetary defense truly began in 1994, when comet Shoemaker Levy 9 slammed into Jupiter in a series of 21 separate impacts over 6 days. Astronomers around the world watched as fragments of the comet, each between 1 and 2 kilometers across, plunged into Jupiter's atmosphere. The collisions produced impact scars in the cloud tops that were larger than the Earth itself. It was a profound and historic event, as it was the first time humans had ever witnessed an extraterrestrial impact in real time. The impression it made was deep and lasting. If a comet of that size could be ripped apart by Jupiter's tides and turned into a string of cosmic bullets, what was to stop a similar object from arriving at Earth instead? That event reignited a debate that had been simmering quietly since the 1960s. How do you defend a planet? The proposals that emerged fell into a few rough categories. When humanity contemplates its defense against cosmic threats, a range of strategies comes to mind. We have conceived of kinetic impactors, which involve deliberately crashing a heavy spacecraft into an asteroid to alter its trajectory. There are also gravity tractors, a more patient method where a spacecraft flies alongside an object for years, using mutual gravity to gently tug it onto a new path. Other ideas include solar sails or reflective coatings, designed to harness the subtle pressure of solar radiation. But for the most dire circumstances, one option has always loomed large: nuclear deflection. Its most vocal proponent was Edward Teller, a pivotal figure in the development of the hydrogen bomb in the 1950s, who remained influential in defense physics throughout his life. Teller's argument was stark and direct. For any sufficiently massive object on a collision course with Earth, the only truly reliable response was to detonate a nuclear device, either near it or within it. The logic was rooted in pure physics. To avert disaster, You must deliver an immense amount of energy in a very short time, and no other technology we can create approaches the efficiency of a nuclear weapon. Conventional explosives are simply too weak, while kinetic impactors require too much advance warning and development time. A nuclear device, however, can be assembled, launched, and delivered in a matter of months, producing a change in momentum that other methods cannot hope to achieve. Within the field of nuclear deflection, two distinct approaches have been studied. The first is known as the standoff burst. This involves detonating the weapon at a calculated distance from the asteroid's surface. The resulting blast of energy instantly vaporizes a thin layer of surface material, and the recoil from this ejected vapor functions like a powerful, improvised rocket engine, pushing the entire object onto a safer trajectory. The standoff burst is considered the gentler of the two options, as its primary goal is to shove the object without shattering it. The second, more aggressive method is the subsurface burst. Here, the device is designed to penetrate the object and detonate from within. This approach is far more energetic and efficient at transferring momentum. If the device is powerful enough, it does more than just deflect the object. It disrupts it completely, breaking it into numerous smaller pieces. The resulting fragments scatter, and by the time they might reach our planet, they would ideally be small enough to burn up harmlessly in the atmosphere, or, at worst, cause only localized damage. It represents a more forceful, and perhaps more desperate, solution. Modern analyses from institutions like NASA and the Department of Energy have explored both of these nuclear options in great detail. A general consensus has emerged, forming a kind of strategic playbook for planetary defense. For smaller objects with many years of warning time, non-nuclear kinetic impactors are deemed sufficient, as demonstrated by NASA's successful DART test in 2022. As the threat level increases, so does the proposed response. For medium-sized objects, or those with shorter warning times, standoff nuclear bursts become the preferred method. And for the most terrifying scenarios, large objects on short timelines, where a simple deflection is no longer possible, subsurface disruption is considered the option of last resort. The goal shifts from moving the object to breaking it apart, accepting that some fragments will likely hit Earth, but reasoning that many small impacts are preferable to a single cataclysmic one. For 30 years, this playbook has been refined, computer-modeled, and stress-tested. It is our best-laid plan, and it is precisely here, within our most trusted strategy, that a brutal and terrifying paradox reveals itself. The very plan designed to protect Earth from a Shoemaker Levy 9 class impact becomes the trigger for an even greater disaster when applied to an object like the one designated 3I, Atlas. The same nuclear device that would safely break apart a common, inert asteroid could instead ignite a deuterium-rich one. Physically, the strategy for disruption and the strategy for ignition are identical. The only variable is the composition of the target, a variable we have, until now, largely assumed to be consistent across all threats. We are therefore left in the precarious position of having a defense plan that works for 99% of plausible scenarios, but fails catastrophically in the worst possible way for the remaining 1%. And that 1% represents the very class of object where a defense plan matters most, because it is the scenario where the threat to our world is at its absolute greatest. This is the planetary defense paradox, and it has no easy solution. Let us now walk through what happens when this paradox plays out. Imagine the scene, because its implications are worth contemplating. A telescope, somewhere on Earth, detects a new interstellar object hurtling through our system. Its trajectory is inbound. After urgent calculations, astronomers confirm it will pass perilously close to Earth, with a high probability of impact. The object is immense, perhaps a kilometer across, or even larger. Worse, it is moving at an incredible speed, around 60 or 70 kilometers per second, a velocity that makes deflection both difficult and time-consuming. The window of opportunity for a kinetic impactor mission has already closed. The only remaining option, the one that is just barely feasible, is nuclear deflection. The world's space agencies confer, and a decision is made under immense pressure. The plan is to use a subsurface nuclear device to shatter the object before it can reach us. This is the standard procedure, the one straight from the Teller playbook. It is the logical choice, the heroic choice. And in this specific scenario, it is the worst possible plan. The mission is launched, and the interceptor spacecraft successfully reaches its target. The penetrator delivers the nuclear device deep inside the object. Detonation occurs. In the fraction of a second that follows, everything changes. A chain reaction that no one planned for ignites a vast reservoir of deuterium that no one knew was there. What was intended to be a controlled disruption becomes an uncontrolled thermonuclear detonation. The kinetic threat we were trying to prevent is instantly replaced by an energy release orders of magnitude larger. In our attempt to save Earth, we have instead sealed its fate. This is not a work of science fiction. This is the scenario outlined in scientific papers, and the physics that underpins it is the same fusion theory used to build the hydrogen bomb. The scenario is not exotic. It is a straightforward consequence of applying our existing tools to a target whose properties we failed to recognize. The grim irony is that the more advanced our defense capabilities become, the more severe this scenario gets. A future Earth with a robust nuclear interception system is also a future Earth with a faster, more reliable trigger for any deuterium-rich object that happens to cross our path. The defense becomes the weapon. The shield transforms into a gun pointed directly at ourselves. What is perhaps most unsettling is the timeline for making such a fateful decision. In a real planetary defense emergency, there is rarely a leisurely window for thorough investigation. An inbound object is typically detected only weeks or months before a potential impact. Attempting to perform spectroscopy on a faint, fast-moving target at a great distance is an immense technical challenge. Obtaining a high-quality measurement of deuterium concentration, the very kind of data that the James Webb and ALMA telescopes produced for 3I, Atlas requires the object to be close enough, bright enough, and outgassing enough for its chemical signature to be detectable. These are conditions that might only be met when the object is already upon us, far too late to reconsider the one strategy we thought would save us. In many realistic scenarios, a decision on whether to deflect an approaching object will have to be made without the spectroscopic data needed to confirm if such an action is safe. This is because many objects will not meet the conditions for clear analysis until it is already too late to do anything but launch a mission. We are thus faced with a terrible choice. Imagine an object is inbound, with a decision needed in just 60 days. The initial low-resolution spectra are ambiguous. It could be a normal comet, or it could be something far more dangerous to interfere with. The conservative path would be to assume it is the more exotic type and not detonate a nuclear device, but this means accepting a kinetic impact. For a large object, that impact alone could spell the end of human civilization. The aggressive move is to assume it's a normal comet and use a nuclear charge, but this risks transforming a kinetic catastrophe into an even more devastating energetic one. There is no clean option, only a choice between two potential disasters made with limited information on an unforgiving timeline. What makes this dilemma so much worse than a standard risk calculation is the profound asymmetry of the consequences. In most planetary defense scenarios, the cost of doing nothing is significant but finite, while the cost of acting incorrectly is generally smaller. With objects of the 3 Atlas class, however, this logic is inverted. The cost of a mistaken deflection could be many times greater than the cost of simply letting the impact happen. This flips the entire risk model on its head. Suddenly, the default conservative move of launching a nuclear interceptor against a threat becomes the very action that dramatically increases the potential for a worst-case outcome. As decision-makers, humans are notoriously poor at navigating these kinds of inverted symmetries. Our instinct is to act, to do something. But, in this case, the right answer might genuinely be to do nothing, because a kinetic impact may be survivable in a way that an energetic detonation is not. There is something almost philosophically unsettling about this conclusion. We have dedicated 30 years to building the institutional and technical capacity to defend our world. The very idea that the wisest course of action, in some scenarios, is to consciously choose inaction is a difficult concept for organizations whose entire purpose is to act. The same political pressures that would compel a launch decision in a real-world crisis would also make it incredibly difficult to advocate for restraint, even in the face of a presumed threat. This raises a disturbing possibility. The defense apparatus we have constructed could itself become the instrument of the very failure mode it was designed to prevent. The shield effectively becomes a gun, with the trigger being pulled by the same people who built the shield. This disturbing thought connects directly back to the central issue. The entire reason we are grappling with this problem is that the object designated 3 Atlas forced us to confront a class of celestial body that our previous models had not accounted for. Its discovery was not merely the identification of a new type of comet to be studied. It introduced a new and catastrophic failure mode for our entire planetary defense architecture. It completely rewrote the risk landscape and forced a question that nobody wants to answer. Can we detect and characterize these objects fast enough to make the right call every single time, especially in a scenario where the wrong call could end the world? Detecting an interstellar object is fundamentally harder than finding an asteroid within our own solar system for reasons that have little to do with the power of our telescopes. These interstellar visitors are moving incredibly fast, often at 30 to 60 kilometers per second relative to the Sun, a speed far greater than the slow, predictable dance of gravitationally bound asteroids. They are therefore typically detected only when they are already deep inside the inner solar system, farther out. They are simply too dim and too small to be distinguished from background noise. This means their appearance is fleeting, offering only a limited window of visibility before they swing around the Sun and fade quickly on their way back out into deep space. For 3 Atlas specifically, this detection window was a matter of weeks to months. While this was more time than Oumuamua offered, which was famously discovered already on its way out, it is still a vanishingly short period in cosmic terms. The process of spectroscopy, the very analysis that revealed the critical deuterium anomaly, requires even more time and more specific conditions. To obtain a clean signal, the object must be at a particular distance and have a sufficient outgassing rate. Furthermore, access to the necessary instruments is a challenge in itself. Time on powerful observatories like the James Webb Space Telescope is heavily oversubscribed and precious. There is simply no guarantee that a targeted observation can be scheduled, executed, and analyzed within a time frame that would be useful for making a defensive decision. The detection bottleneck is a very real problem. Fortunately, there are efforts underway to fix it. NASA's NEO-Surveyor mission, an infrared space telescope scheduled for launch in the late 2020s, is specifically designed to find near-Earth objects, a category that will naturally include interstellar visitors passing through our region of space. In addition, the Vera Rubin Observatory in Chile, which began full science operations in 2025, is poised to massively increase the rate at which we discover new objects in the solar system, including interstellar ones. We are going to find more of these objects likely, a lot more. The frequency with which we catalogue interstellar visitors is set to increase by orders of magnitude within the next decade. But, And this brings us back to the central thread. Detection is not characterization. Discovering that an object exists is not the same as knowing what it is made of. A wide-field survey telescope can spot a moving point of light against the background stars and confirm its interstellar trajectory. However, it cannot by itself tell you if that object is enriched in deuterium. For that, you need spectroscopy. You need the object to be outgassing. You need it to be bright enough, close enough, and active enough to produce a detectable signal. The problem is that those conditions do not always overlap with the critical window in which a defensive decision has to be made. This disparity highlights a crucial concept I want to flag: the operational gap. This is the difference between the rate at which we can detect interstellar objects and the rate at which we can characterize them well enough to make an informed, defensive decision. Detection is getting faster, but characterization is not. This gap is widening, and it is within this gap that the worst-case scenarios reside. If you detect an object, see that it is on a collision course, and have to decide what to do without knowing if it is deuterium-rich or not, you are trapped in that impossible situation where you might pull the wrong trigger. This connects everything back to our central dilemma. Identifying whether an object is safe to deflect has now become as critical, and perhaps even more critical, than detecting the object in the first place. Simply detecting an interstellar visitor is not enough. It provides incomplete information. To act on such information in this domain, where the consequences could be civilization ending, is a profound risk. This reality demands a fundamental re-evaluation of our priorities, our budgets, and our allocation of precious telescope time. We require more than just detection. We need a capacity for rapid response characterization. This means having spectroscopy available on demand, with targeted infrared and millimeter follow-ups for every interstellar object the moment it is discovered. We need established protocols to deliver spectral data into the hands of decision-makers within days, not months. The sobering truth is that the infrastructure for this barely exists. The funding is almost entirely absent, and generating the political will to build it requires those in power to seriously consider a threat that, prior to 2026, would have sounded like a premise from science fiction. A clock is ticking, and we were unaware it had even started until the arrival of 3I. Atlas forced us to listen. Before exploring any extraordinary hypotheses, intellectual honesty demands that we construct the most robust possible case for a natural explanation. This is not about simply labeling the chemistry of 3I, Atlas, as weird. It is about diligently working through the strongest scientific argument for how nature could have produced it. Only after we have exhausted this path and tested its limits can we justify turning our attention to any other possibility. This rigorous process must be our guide. The strongest natural case begins its journey in the coldest and densest regions of the interstellar medium. Within vast molecular clouds are pockets of extreme density and cold, known as prestellar cores, the very cradles where new stars and planetary systems are eventually born. They are colder than almost anywhere else in the galaxy, with temperatures in their interiors dropping to around 10 Kelvin or even lower. By cosmic standards, they are also incredibly dense, containing enough gas and dust to slow most chemistry to a crawl, while simultaneously enabling certain reactions that cannot happen anywhere else. Inside a prestellar core, a slow but persistent form of ion molecule chemistry unfolds over hundreds of thousands of years. During this time, deuterium becomes concentrated into specific molecules through a process called fractionation. The underlying mechanism is a subtle thermodynamic effect that only becomes significant at extremely low temperatures. Chemical reactions involving deuterium are slightly more exothermic, releasing a tiny bit more energy than those with normal hydrogen, because the bonds they form are slightly tighter. At room temperature, this difference is insignificant, lost in the background thermal noise. But At 10 Kelvin, this tiny difference becomes a major driver of chemistry. Specific reactions, like the conversion of the trihydrogen cation to its deuterated form, are driven preferentially in one direction. Over immense timescales, deuterium accumulates in molecules such as ammonia, methanol, formaldehyde, and indeed, methane. This is not merely a theory. Astronomers have observed this enrichment in real prestellar cores, confirming that the chemistry is sound. The role of dust grains adds another layer to this process. In the frigid, dense interior of a prestellar core, atoms and molecules adhere to the surfaces of these tiny grains. Hydrogen and deuterium, in particular, accumulate on the grains and then react with other elements like carbon, oxygen, and nitrogen that are also stuck there, forming complex molecules. This grain surface chemistry serves as another amplifier for deuterium. Being heavier and slower, deuterium atoms tend to remain on the grains for longer periods, which increases their chances of being incorporated into the molecules being constructed. The ultimate result is that the icy coatings on these grains can become substantially richer in deuterium than the surrounding gas. When these ices are later liberated, either through star formation or collisions, they can form bulk material that carries a distinct chemical memory of this prestellar enrichment. So, the Steelman argument proposes this. 3I, Atlas may have formed in an environment that was extraordinarily cold, exceptionally dense, and chemically active for an incredibly long time. The combination of low-temperature ion molecule chemistry in the gas phase and the accumulation of material on grain surfaces could, in principle, produce matter with elevated deuterium ratios. It is conceivable that if the conditions were extreme enough and persisted long enough, they could create material far more enriched than anything we have measured elsewhere. However, this natural explanation encounters a significant problem, and it is a problem of scaling. While we have measured deuterium enrichment in prestellar cores, this enrichment is typically a surface-level phenomenon, a thin coating on dust grains, not the entire mass of a developing object. To produce a kilometer-scale body like 3I, Atlas, that is enriched throughout its bulk to the levels observed, you would need either a far more efficient method of incorporation than our current models suggest, or a completely different formation pathway than the standard pipeline from a prestellar core to a comet. There is also the temperature ceiling problem. The cosmic microwave background radiation establishes a temperature floor for the universe, currently at roughly 2.7 Kelvin, while strong shielding can allow local regions to dip below this briefly. Maintaining bulk material below 10 Kelvin for the vast timescales required to enrich it to the levels seen in 3I, Atlas presents a significant challenge. Our models can only produce such conditions at the extreme edge of plausibility. It is not impossible, but it is at the very boundary of what we consider possible. And nature, while capable of remarkable feats, does not generally operate at the edge of impossibility without a compelling reason. This is what it means to say that even the best natural explanation is strained. It struggles to justify an object that behaves like a concentrated energy system. The chemistry might be able to do it, but only if you push every single parameter to its absolute limit. And an explanation that relies on pushing every variable to its extreme is not the same as a likely one. The natural explanation remains a possibility, but it is not a comfortable one. It is the one we must strive hardest to validate, if only to be certain we have exhausted all other options before considering the alternatives. There is, however, another natural hypothesis that warrants consideration, one rooted not in extreme chemistry, but in extreme age. This is the idea that 3I, Atlas, may have originated within a population 2 stellar environment. These are the older, low metallicity stars and protoplanetary disks that formed much earlier in the history of the universe. Population 2 systems have lower abundances of heavy elements compared to population 1 stars like our Sunday. This means their primordial gas was closer to the original composition of the Big Bang, a composition that, crucially, had a higher initial deuterium to hydrogen ratio to begin with. Perhaps the answer lies not in how the object was processed, but in the ancient, primordial material from which it was made. If we combine that primordial advantage with the minimal stellar processing found in such early star systems, a plausible argument begins to form. An ancient object from that kind of environment might carry an elevated deuterium ratio simply because it has been preserved since an era when deuterium was far more abundant across the cosmos. Yet, this hypothesis confronts a formidable obstacle, one rooted in the fundamental challenges of transport and survival. For an interstellar object to journey from a population 2 system all the way to our own, it would have to survive intact for billions of years, drifting through the vastness of interstellar space. It would need to avoid being captured by other stars, withstand the relentless bombardment of cosmic rays, and remain cool enough to not lose its precious chemical enrichment. This represents an extraordinarily long time to wander through a hostile galaxy, raising a profound question of sheer probability. Most of the material ejected from those ancient systems almost certainly does not complete such an epic journey. The fraction that could possibly survive long enough to be detected by a young species like our own on a planet orbiting a population 1 star, all within the fleeting window of our existence, must be incredibly small. This realization connects back to a central, sobering theme. Regardless of its exotic natural origin, the object's properties make it a potential hazard. Whether 3I Atlas came from an ancient, low metallicity system, a peculiar prestellar core, or some other place entirely, the practical implication is the same. It is enriched, it is reactive, and should the next one we see be on a collision course, treating it as a normal target could have devastating consequences. The exotic origin hypotheses do not solve the planetary defense problem. They simply reveal that the universe is larger and stranger than our models accounted for, and that the population of risky objects out there is more diverse than we once feared. Now, we must give the skeptical reading a full and fair hearing, because skepticism is a core virtue of the scientific method. The strongest possible challenge to a claim is what allows it to either stand or fall. The skeptical response to the 3I Atlas measurements would be that the reported deuterium ratios rely on spectroscopic techniques which are known to be susceptible to systematic errors. This viewpoint urges caution, reminding us that we should be wary of treating any single measurement as the final word, even when it comes from instruments as magnificent as the James Webb Space Telescope and ALMA. Spectral lines, for instance, can be misidentified. It is possible for 2 distinct molecules to possess features at very similar wavelengths, and confusing one for the other would lead to fundamentally incorrect ratio measurements. While the spectroscopy of deuterated water and methane is well characterized in laboratories, the conditions in deep space, the unique temperatures and densities of the gas surrounding 3I Atlas can produce line profiles that differ from these laboratory standards. If a feature attributed to a deuterated species is actually being generated by something else, then the inferred ratio is simply wrong. This is a real and valid concern that any responsible spectroscopist would consider. Calibration is another potential source of error. The instruments must be calibrated against known references, and any drift in this calibration can shift the inferred abundances. The James Webb Space Telescope is an extraordinarily well-calibrated instrument, but it isn't perfect, and at the very edges of its sensitivity, errors can creep in. ALMA is similarly well-calibrated, but the very act of combining 2 datasets from 2 different instruments, each using its own calibration pipeline, introduces its own layer of systematics. Finally, there are the inherent limitations of the instruments themselves. Both Webb and ALMA have finite resolution and finite sensitivity. Faint lines can be difficult to detect cleanly, while strong lines can saturate the detectors. The deuterium features being analyzed are not the easiest things to measure in the universe, so a skeptic could reasonably ask whether the reported ratios are being pushed beyond what the instruments can confidently support. Here, however, we find the counter-argument, and it is what makes the 3I Atlas measurements so uncomfortable to dismiss. The two observatories are independent. They use entirely different physical principles. Webb measures infrared transitions, while ALMA detects millimeter wave rotational lines. They are operated by different teams with different analysis pipelines and are subject to different sources of systematic error. Despite all this, both observatories returned anomalously elevated deuterium ratios, and they did so for different molecules. The probability that two independent systematic errors in two independent measurements would just happen to produce consistent enrichment by a factor of 1,000 is not zero, but it is remarkably small. Moreover, the cross-molecule consistency with both water and methane being elevated, and methane more so, as predicted by low-temperature fractionation, fits the physical picture of an enriched object far better than it fits any plausible error scenario. Of course, future observations could absolutely shift these numbers. A more refined analysis might lower the inferred enrichment, and independent measurements from other instruments could either confirm or weaken the signal. The science is not closed, but this is where the central thread reasserts itself. Even if the values were to shift downward by a factor of 3 or 5 or even 10, the object would still be dramatically enriched relative to anything else we have ever seen. To make 3I Atlas look like a normal comet, you would need to revise the ratios by 2 full orders of magnitude. That is not a calibration error. That would be a complete misreading of the data, and the chances of such a mistake are extremely low. So, while skepticism is warranted and ongoing measurement is essential, the skeptic's exit does not get you all the way out. The window for dismissing this object as a measurement artifact has effectively closed. We are stuck, one way or another, with a real anomaly. This brings us to the hypothesis that no one likes to discuss in polite company, but which the data compels us to place on the table: the technosignature hypothesis. A technosignature is a sign of technology specifically, the kind of sign that would be produced by a technology and not by natural processes. The classic technosignature was always imagined to be a radio signal, a beacon from another civilization. But the modern conception has expanded to include any anomaly in the natural world that suggests an engineered origin. This might be a weird spectrum from a star, a strange chemical signature in an exoplanet's atmosphere, a comet that maneuvers without venting gas, or a composition that mirrors what we ourselves would build if we wanted to accomplish something specific. I want to be careful here, because the technosignature hypothesis is not a claim. It is, rather, an acknowledgement that when the data becomes this unusual, the possibility of an artificial origin must be considered as part of a thorough scientific inquiry. It is important to begin with a clarification. This is a hypothesis. The paper by Dr. Lowe does not assert that 3I Atlas was an engineered object. Instead, it meticulously analyzes the physics of what would occur if such an object were on an inbound trajectory, treating it as a potential threat. Yet, the possibility of a technosignature is embedded within the data itself, waiting for consideration. Whether we find the idea comfortable or not, the scientific method requires that this hypothesis be evaluated on its own merits. So, let us explore the case for this extraordinary possibility, laid out as clearly as the evidence allows. At the heart of this hypothesis lies the element deuterium, which is widely considered the ideal fuel for fusion propulsion. Every significant concept for a fusion drive in the engineering literature, from the ambitious Project Daedalus of the 1970s to contemporary proposals involving inertial confinement and magneto-inertial designs, is based on enriched deuterium. Sometimes, It is combined with helium-3 or tritium to enhance efficiency. The logic is compelling. Deuterium is the lightest element capable of fusing with high efficiency. This physical reality means that you can extract more energy per kilogram of fuel mass than with any other viable alternative. If a civilization wishes to traverse the stars in a reasonable time frame, a fusion drive is the most logical choice. And for a fusion drive, you need a substantial supply of enriched deuterium. Viewed through this lens, the composition of 3I, Atlas begins to look like a reservoir of fuel. The observed levels of deuterium enrichment fall within a range that would be logical for an engineered supply intended for fusion reactions. Furthermore, the ratio of methane to water in the object's deuterium fractionation seems more consistent with a process of deliberate concentration than with any known process of random, natural enrichment. Adding to this picture is the object's journey itself. The fact that 3I, Atlas, is an interstellar body moving through our solar system on a hyperbolic trajectory aligns with what one might expect from a lost fuel pod or a damaged interstellar craft, now drifting silently through the galaxy. The argument gains strength when we consider the convergence of evidence, a concept sometimes called pattern stacking. Beyond its unusual deuterium enrichment, 3I, Atlas exhibits several other characteristics that certain researchers have identified as deserving a closer look. These include subtle anomalies in its trajectory and patterns of outgassing that do not conform to standard models of cometary behavior. While no single one of these anomalies is conclusive proof of anything, their combination seems to fit a technosignature interpretation more comfortably than it does any single natural explanation. This is the essence of pattern stacking. The collective weight of suggestive evidence can point toward a conclusion that no single piece of data could support on its own. Of course, a healthy dose of skepticism is essential, and there are perfectly reasonable objections to the technosignature hypothesis. The human mind is prone to confirmation bias. Once you begin searching for signs of engineering, you may start to see them everywhere. The principle of parsimony, often called Occam's razor, suggests we should favor the simplest explanation. A natural origin, even a strange and strained one, is almost always simpler than an engineered one. We also face a limitation in our data. With a sample size of only 3 known interstellar objects, drawing broad conclusions about engineered origins is statistically precarious. And we must not forget the lessons of history. Astronomy is filled with initially mysterious phenomena, like pulsars and fast radio bursts, that were once speculated to be alien signals before we understood the natural processes, like rotating neutron stars, that created them, for very good historical reasons. Astronomers are professionally conditioned to be deeply skeptical of such claims. The most honest scientific position on 3I, Atlas, therefore, lies somewhere in the middle. The technosignature hypothesis is far from proven, but it has also not been ruled out. It remains a possibility that is worthy of serious consideration, of further investigation, and of being factored into the design of future observations and searches. This is not a hypothesis to be embraced as a final conclusion, nor should it be reflexively dismissed. Both reactions, the credulous acceptance and the dismissive rejection, represent a failure of intellectual discipline. The correct path is to hold the hypothesis open, to commit to gathering more data, and to allow that data to guide us toward an answer. This entire discussion connects back to a much harder, more immediate reality, because regardless of which origin story you find more plausible exotic natural chemistry, an ancient low metallicity origin, simple measurement error, or a technosignature, the operational implication remains identical. The fact is, 3I, Atlas, is profoundly enriched in deuterium. This means the next object like it, should it appear on a collision course with Earth, will present a formidable problem. We must begin to plan as if these objects are real and as if they are reactive because the data shows they are. The fascinating question of who or what might have made them is ultimately secondary to the urgent question of what we will do when one of them is heading our way, and we must decide whether to act. For decades, our model of the asteroid threat has been governed by a single, dominant variable: kinetic energy. The destructive power an object delivers upon impact is calculated from its mass and its velocity. That is the complete equation. A large, fast-moving rock equates to a major problem. A small, slow-moving one does not. It raises the question, was this framework ever truly sufficient? Every aspect of our planetary defense thinking, from the models we run to the budgets we approve, has been built around this core calculation. Every simulation ever funded in a space agency boardroom has been a variation on that one theme. We assess threats based on their potential impact energy. We design our responses, whether deflecting the object to make it miss, or breaking it up into smaller fragments for the atmosphere to handle specifically to mitigate that kinetic energy. Over the last 30 years, we have constructed an entire industry of hazard assessment that exists wholly within this kinetic energy paradigm, and now that entire way of thinking has just been revealed as incomplete. 3I. Atlas broke the paradigm. It did not do so by being more dangerous in the familiar kinetic sense, but by hinting at a kind of danger that nobody was even modeling. The kinetic energy of an object the size of 3I, Atlas, striking Earth at a typical interstellar speed of around 60 kilometers per second would be substantial. The impact would be terrible, but it would be a bounded catastrophe, releasing energy on the order of a few teratons of TNT equivalent. This is comparable to major impact events in our planet's geological past, devastating for the continent it struck, but survivable for the human species as a whole. It would not be a civilization-ending event. This kinetic threat profile is what we have spent 3 decades preparing for. It represents the worst-case scenario detailed in every defense planning document on every desk in every space agency on Earth. But the reactive threat is something else entirely. The reactive threat is what happens when the kinetic energy of an impact is dwarfed and completely overwhelmed by the chemical or nuclear energy stored inside the object itself. It introduces a new and far more unsettling variable into our planetary defense equation. Imagine a hypothetical scenario where the deuterium reservoir within 3I, Atlas, were to ignite under just the right conditions. The result would be an astonishing energy release of approximately 10 teratons, an output several times greater than the object's own kinetic energy. The truly critical detail, however, is not the sheer magnitude of the blast, but its nature. This energy would not be delivered as a conventional ground shock from a physical impact. Instead, it would manifest as a devastating wave of pure radiation, a blinding flash of light, neutrons, gamma rays, and superheated plasma. The damage profile from such an event is fundamentally different from a kinetic impactor, meaning the required defensive response is also fundamentally different. We are not simply dealing with a bigger version of a known problem. We are confronting an entirely new kind of cosmic threat. To properly contend with this new reality, our scientific vocabulary must also evolve. A new term is needed, one that the field has yet to settle on, but for which we might propose energy-bearing body. This designation would apply to any celestial object containing stored chemical or nuclear energy in quantities so large that, if released, this internal energy would dominate the object's entire threat profile. In all of human astronomical history, 3I, Atlas is the first object to be confirmed as an energy-bearing body. Its discovery carries a profound implication. If one exists, there are almost certainly others, drifting silently and unseen between the stars. In the span of a single peer-reviewed paper, our perception has shifted from a universe where incoming objects are presumed inert to a more complex reality where a fraction of them must now be considered potentially volatile. This represents a categorical shift in how we must approach the calculus of cosmic risk. The strategic consequences of this realization are immense, cascading outwards in every direction. A composition-first approach to analysis now becomes absolutely essential. It is no longer sufficient to merely know an object's size and speed. Consider two intruders of identical mass and velocity approaching Earth on the exact same trajectory. One might be a standard stony asteroid that we could safely disrupt or break apart. The other, however, could be a deuterium-rich body that we must not, under any circumstances, touch with a nuclear device. This single possibility reveals that the established kinetic energy paradigm, the very foundation of our planetary defense strategies for decades, is insufficient on its own. It must be urgently augmented, or, in some cases, completely replaced by a new model centered on an object's internal chemistry. This is not a simple adjustment. It is vital to be clear about just how monumental this task is, because it is the part of the problem most easily overlooked. Determining an object's composition from a great distance is an order of magnitude harder than measuring its mass and velocity. An object's mass can be reasonably inferred from its brightness and assumed reflectivity, while its velocity can be measured with high precision through astrometric observation of its trajectory. But composition requires spectroscopy, the intricate science of analyzing the light an object emits or reflects to reveal its chemical secrets. The challenge is that the universe does not always cooperate. Many objects, especially the inert ones we are trying to rule out, are dim, dark, and remain chemically silent until they are practically upon us. This creates a terrifying paradox. The point at which an object is close enough for its composition to be properly characterized is often the same point at which it is far too close for any meaningful defense to be mounted. The problem of measurement and the problem of response are tightly coupled, and this coupling only grows more desperate as the object gets closer. We could find ourselves with less time to act and less information to act upon simultaneously. The central operational challenge of this new era, therefore, is one of classification. We urgently need a system to look at an inbound object and quickly, reliably, and robustly determine if it is a simple kinetic threat or a volatile reactive threat. This requires establishing new, agreed-upon standards for what constitutes evidence of reactivity. It demands decision protocols that explicitly integrate compositional uncertainty into their risk calculations, rather than treating composition as a known and fixed quantity. We also need a chain of command that can act decisively on incomplete information without making a catastrophic error, and one that can also resist the inevitable political pressure to do something when the wisest course of action is to wait. Critically, this entire infrastructure, the standards, the protocols, the command structure, must be fully established times before times the next 3I Atlas-class object appears on our screens. In the heat of the moment, with the clock running down and an object hurtling through space, there will be no time to design a system from scratch. We will be forced to use whatever system is already in place. If we have built nothing, we will be left to improvise. And improvisation in this context is precisely the kind of gamble that recent scientific warnings caution us against. The unforgiving physics of the situation does not care about our institutional capacity or our state of readiness. The universe will deliver the next interstellar object on its own schedule, with no regard for whether we are prepared. The outcome of that encounter will be dictated by the actual composition of that object, not by our intentions, our hopes, or our incomplete reading of the data. The sole job of planetary defense is to align our response with that underlying physical reality. As 3I, Atlas revealed with brutal clarity, that alignment is currently broken. Fixing it will be the defining work of the next decade, assuming we are lucky enough to have a decade before the next reactive object shows up. The policy implications that radiate from this problem are as vast as they are uncomfortable. International agreements, such as the Outer Space Treaty of 1967, were written under the assumption that nuclear options in space were only for hypothetical asteroid deflection. These treaties may now need to be revisited carefully. The science budgets of the world's space agencies, which currently devote relatively little funding to characterizing interstellar objects, may need to be substantially rebalanced toward rapid response spectroscopy and follow-up missions. Furthermore, civil defense planning, which is essentially non-existent for thermonuclear scale events outside the context of human warfare, may need to acknowledge a new category of natural risk that involves no human enemy at all. None of these conversations are easy, but they are now unavoidable. The discovery of 3I, Atlas, compels a re-evaluation of our place in the cosmos, connecting every observation back to a central, unsettling theme. We have been confronted with a type of hazard we never knew was possible, and the time we have to prepare for it may be far shorter than we would hope. This brings us to a fundamental statistical dilemma. In the entire history of human observation, we have confirmed only 3 visitors from beyond our solar system. Just 3 instances. On 3 separate occasions, an object from interstellar space passed closely enough for us to identify its origin. This constitutes our complete dataset. And of those 3, one is so profoundly and uniquely anomalous that if it represents a common class of object, it signifies a new kind of existential risk to civilization. So, how are we to interpret this statistically? The most honest answer is that we simply cannot, and this very uncertainty is the core of the problem. It is a situation worth pausing to consider, as it is genuinely without precedent in most scientific endeavors. Typically, scientific conclusions are built upon vast foundations of evidence, thousands of measurements, or millions of data points, allowing clear patterns to emerge from the background noise. In the study of interstellar objects, however, our entire body of knowledge rests on a sample of 3. And one of these 3 objects behaves in a way that defies every model we currently possess. The relationship between signal and noise in our understanding has been inverted. We have more anomaly than we have a stable baseline. Every conclusion we attempt to draw is derived from a population size equivalent to a small, quiet gathering. This raises a profound question. How can we build a reliable understanding of an entire population from such a fragile and contradictory starting point? There are a few ways to interpret the 1 in 3 statistic, and each path forward carries its own significant consequences. The first interpretation suggests that interstellar objects with extreme deuterium enrichment, like 3I Atlas, are actually quite common. If this is the case, then 3I Atlas is merely a typical example of a large, underlying population. This would mean we should anticipate seeing another one soon, perhaps in the coming years or even months, especially as new survey telescopes increase our detection capabilities. Should this prove true, our planetary defense systems are in a dangerously exposed position. We possess no established protocols, no rapid characterization pipelines, and no decision-making frameworks for how to handle such reactive objects. We would essentially be navigating the future with an outdated and incorrect guide. A second interpretation offers a different perspective, that interstellar objects with these unusual properties are, in fact, exceptionally rare. In this view, we were either incredibly fortunate or unfortunate, depending on your outlook, to have detected one so early in our search. If this scenario is accurate, it grants us more time. The threat remains real, but the urgency is less immediate. The next reactive object might not appear for decades or even centuries, giving us a crucial window to develop the right technology, train the necessary experts, and implement sound policies. This is, admittedly, the more reassuring conclusion. Yet, it is precisely for this reason that it should be met with skepticism. Comforting narratives have a tendency to prevail in policy discussions, even when they are not strongly supported by the available data. A third possibility is that a powerful detection bias is fundamentally shaping our limited sample. The very conditions that allow us to spot an interstellar object, namely, the outgassing activity that makes it bright enough to see and chemically complex enough to analyze, might be intrinsically linked to the processes that create extreme deuterium enrichment. If this is true, it would mean that these chemically enriched objects are dramatically overrepresented in our tiny dataset. The true interstellar population might contain far more mundane, inert bodies that are kinetically dangerous but chemically unremarkable. In this interpretation, 3I, Atlas, is the loudest member of a much quieter, larger crowd. This carries its own troubling implications, as the quietest objects are the ones we are most likely to miss until they are already upon us. The fourth interpretation, which synthesizes elements of the others, is that we genuinely have no basis for knowing the true distribution. Our sample is far too small to place any meaningful constraints on it, and to pretend otherwise would be a form of intellectual evasion. This fourth view is, I believe, the correct one. It is also the most disquieting, because it acknowledges that we have absolutely no statistical leverage over the population of interstellar objects. We do not know how many are passing through our solar system at any given time. We have no clear picture of their aggregate compositions. We cannot say how many are reactive versus how many are inert. With only 3 data points, one of which is a significant outlier, we have essentially zero power to answer these critical questions. And yet, we are being asked today to make decisions about planetary defense and civilizational risk based on statistical knowledge that simply does not exist. We are flying without instruments, forced to choose without information. This problem of detection bias warrants a much closer examination because its effects are more profound than many realize. Consider for a moment why we were able to detect 3I, Atlas, in the first place. The answer lies in its activity. It was outgassing. We could observe its deuterium signature because the object was actively venting material, and this plume was bright and chemically distinct enough for our spectrographs to read. A passive interstellar object, one that drifts silently through the solar system without any outgassing, would be far more difficult to spot. It would also be nearly impossible to characterize chemically. At best, we might see a faint point of light moving against the backdrop of stars, but we could not tell you if it were made of ice, rock, metal, or something far stranger. Consequently, our sample of 3 is heavily skewed toward objects that are active and shedding their compositional secrets into space for us to observe. The truly inert travelers are effectively invisible to our current methods. We are unable to count them, and we cannot study them. They represent, in a very real sense, the dark matter of the interstellar object population. This hidden majority could be vastly more numerous than the active objects we are able to see. It is entirely possible that hundreds of inert objects pass through our solar system every year, completely undetected and uncharacterized, their existence unknown to us. And within that unseen population, what kind of compositions might exist? How many of them could be reactive in the same way as 3I, Atlas? How many might be something else entirely? This is the heart of the issue. Our current knowledge is biased toward the noisy end of the spectrum, leaving us blind to the silent majority. Our cosmic census is shaped by what we can detect, and we primarily detect objects that announce their presence by outgassing. This means there is a vast, unseen population of silent drifters, cold, dense bodies that vent no material and reflect very little light that remain completely absent from our catalogues. This observational bias makes it impossible to answer a fundamental question. Is 3I, Atlas, a rare, reactive object, or is it just one of many? The honest answer is that we do not know. The statistical evidence is far too thin to support either conclusion, leaving us with a profound sense of uncertainty about what truly populates the space between stars. And yet, the discovery of a single confirmed example can be enough to reshape our entire understanding. Before the arrival of 3I, Atlas, the probability of finding an object with its extreme deuterium enrichment was considered effectively zero. We had no direct observations of such a body, and no theoretical framework predicted its existence. Based on our models, there was no reason to believe such an object could even form. But after 3I, Atlas, that probability is no longer zero. Quantifying it with so few data points is challenging, but it is undeniably greater than it was before, and it continues to grow as the implications are more carefully considered. This is a perfect illustration of Bayesian updating. In the absence of a guiding theory, one concrete example is enough to elevate a possibility from speculation to a serious scientific inquiry demanding a response. This statistical void is not merely an academic puzzle. It translates directly into operational risk for planetary defense. The fewer data points we possess, the more cautious our decision-making must become. This forces us to assume that any unidentified object heading toward our planet could be reactive, just like 3I, Atlas. This potential for reactivity must now be factored into every single planetary defense scenario we develop. We are compelled to do this without the benefit of reliable population statistics, without established protocols for characterization, often with very little warning time, and lacking the close-range data that would have definitively answered our most pressing questions. The stakes are immense when navigating a threat that is so poorly understood. The final chapter of this story is an uncomfortable one, and there is no way to soften its conclusion. We learned a tremendous amount from 3I, Atlas, just enough, in fact, to become deeply concerned. We learned that the universe contains a class of object that our models had never anticipated. We discovered that our planetary defense playbook has a critical failure mode we had not foreseen. And we learned all of this just in time to watch the object recede back into the void, taking with it any chance of a detailed, close-range investigation that might have resolved the very questions it forced us to ask. That is the part that will haunt this field for years to come. We saw it, we measured it, we grasped its profound implications, and then we could only watch it leave, knowing another opportunity, like it may not come for a very, very long time. Part 17. The window closed. The object known as 3I, Atlas, is now more than 1 billion kilometers from the Sun and continues to accelerate. It is traveling on a hyperbolic trajectory that will carry it back into the interstellar darkness from which it emerged. With each passing day, the window for high-precision observation has narrowed significantly. As for any kind of close-range investigation, a flyby, a probe, or a sample return mission, that window was always brief, and for all practical purposes, it is now completely shut. Its departure feels final, a silent journey away from the star that briefly illuminated its secrets. We will continue to monitor the object for as long as our most powerful telescopes, both on Earth and in orbit, can detect its faint signal. However, the kind of detailed measurements that were possible during its closer approach are now a thing of the past. The spectra that revealed the Deuterium anomaly, the outgassing studies that hinted at its strange chemistry, and the trajectory refinements that informed every subsequent calculation are no longer achievable. The light from this enigmatic visitor is fading, and with it fades our last real chance to ask it any new questions. It is worth dwelling on what we did not do, because the scientific community will be reckoning with this missed opportunity for a long time. As 3I, Atlas made its pass through the inner solar system, quiet but urgent conversations were taking place behind the scenes. In workshops, on email threads, and in hastily convened meetings, some scientists argued that we should send a probe. Even a fast-moving interceptor, launched immediately, would have struggled to catch 3I, Atlas, given its incredible speed. But the proposals, based on concepts like bridge or comet interceptor, were serious. For a brief electric moment, 3I, Atlas was a real, tangible target. Ultimately, the decision not to launch was not driven by a lack of scientific curiosity, but by inescapable practical constraints. There was no mission ready to go, no spacecraft sitting on a launch pad awaiting a target of opportunity. No funding existed for an emergency interplanetary launch on a timeline measured in weeks. The political and institutional processes for approving such a mission are slow, far slower than most people realize, and the object was moving far too fast. By the time anyone could have pulled the necessary levers to secure funding, build consensus, and get a spacecraft launched, the object was already accelerating past the orbit of Mars on its way out. The window of opportunity closed before the bureaucracy could even open. The unromantic truth is that we did not fail to act because we failed to understand the object's importance. We failed to act because the systems we have built for making these decisions were not designed for this kind of timescale. It represents a profound missed opportunity, a fact that everyone in the relevant fields understands. A close-range measurement of 3I, Atlas, would have been completely transformative. We could have sampled its surface directly and measured its composition without having to infer it from distant gases. We could have searched for additional anomalies that remote spectroscopy can never reveal, such as structural features, density variations, or magnetic properties, details that only become apparent when you are physically next to an object. It was our one chance to answer our questions with certainty, and it has now slipped away into the dark. The departure of 3I, Atlas, leaves us with a profound sense of what might have been. A close encounter could have resolved the fundamental question of its nature. Was it merely a natural object at the far edge of known cometary chemistry? Or was it something else entirely? Something for which we do not yet have a name? Instead of answers, we are left with fragments. Remote spectral data, observations from a few precious weeks of telescope time, and a theoretical paper from a Harvard astrophysicist who pursued calculations others had not. The picture remains frustratingly incomplete as the object recedes, leaving a trail of unanswered questions in its wake. We are left to wonder about its internal composition. Is it a single, uniform body? Or is it layered with different materials at various depths? The distribution of its unusual deuterium enrichment is another enigma. It could be spread evenly, or perhaps it is concentrated in a core, a shell, or in isolated pockets that are impossible to map from light years away. Without detailed knowledge of its internal structure, we cannot determine the precise threshold that might trigger its ignition. And perhaps most soberingly, we have no way of knowing if other, similar interstellar visitors have already passed through our solar system, drifting silently through the void while our attention was focused elsewhere. We cannot say how often such objects arrive, nor how many might be traversing the darkness at this very moment. In a rigorous statistical sense, we are facing an unknown. We have only a single example, the barest outline of a problem, and a long list of measurements we wish we had taken. This absence of data leads us directly to the heart of the matter, and it is a point worth making with absolute clarity. The brief appearance of 3I, Atlas, provided just enough information to identify a new category of potential threat, yet it offered far too little to allow us to characterize that threat with any real precision. We now have a name for this problem, but we possess no solution. We have a working hypothesis about what this object might represent, but no means to verify it. This leaves us confronting a stark planetary defense paradox, a challenge for which we are unprepared. As of now, there is no resolved policy response to this dilemma, not from any major space agency, not from any international governing body, nor from the scientific advisory councils tasked with contemplating these exact kinds of risks. We are therefore left in a state of watchful waiting, hoping that the next interstellar object to grace our skies will provide more information, while simultaneously fearing what that new information might reveal. It is a strange and deeply uncomfortable position for any civilization to find itself in. The state we find ourselves in is one of asymmetric knowledge, which is perhaps the most unsettling kind of knowledge to possess. We have learned just enough to be deeply concerned, but not nearly enough to act with confidence. It is a dangerous middle ground. We can describe this new potential threat in general terms, but we are unable to quantify its probability or its potential impact. We can see the potential failure points in our existing planetary defense strategies, but we cannot definitively rule them in or out. Consequently, the very institutions of human civilization, the space agencies, the scientific councils, the international policy groups responsible for considering long-term civilizational risk, are now burdened with preparing for a threat category that, until April of 2026, was not even a consideration. The necessary conversations are slowly beginning to happen in the appropriate forums. Scientific papers are being drafted, and follow-up observation campaigns are being scheduled. The next generation of survey telescopes is being calibrated to specifically search for objects like this one. But the catalyst for all this activity, the object itself, is now gone, and we will not get a second chance to study it. Whatever lessons 3i, Atlas, could have taught us, it has already taught us all it is going to. There is one final, crucial point that frames this entire event in a much larger context. It is, I believe, the most significant truth to emerge from this encounter. We are the first generation of humanity to look into the cosmos and witness something that we cannot confidently place within our existing categories of natural objects. This is no small distinction. Previous generations observed comets, asteroids, meteors, and the puzzling behavior of distant stars. In time, they were always able to fit what they saw into a known scientific framework. Sometimes that framework had to expand, at times dramatically, as it did when we first understood that galaxies were distant island universes, or when we discovered the accelerating expansion of the cosmos, or when we located the first planets orbiting other stars. But in every case, the framework of our understanding eventually closed around the new observation. The phenomenon was given a name, assigned a category, and assimilated into our model of the universe. With 3i, Atlas, however, that framework has not yet closed. In fact, there is a distinct possibility that it will not close within our lifetimes. We simply do not know what we saw, and we are not sure we ever will. And as we sit with this profound uncertainty, with our scientific models left hanging open, we know that other objects are drifting between the stars on trajectories we have not yet detected. Statistically, some of them are likely similar to 3i, Atlas. Others are probably more extreme, more enriched with volatile materials, more reactive, and stranger still. Inevitably, one of them will be on a path that brings it near our planet. Whether this happens in 10 years, 100, or 1,000 is not the most important variable. What truly matters is that on that day, whoever is on duty at the relevant telescope, in the critical control room, or at the responsible agency will be forced to make a decision. They will have to act based on whatever incomplete information is available, within whatever brief window of time the object's velocity permits, and using whatever institutional and political tools their generation has managed to build. The choice they make in that moment could well determine the future of our civilization. This, then, is the ultimate legacy of 3i, Atlas. It is not the object itself, which is already fading from view and will soon be forgotten by most. Its true legacy is the fundamental question it has left in its wake, a question that challenges one of our deepest assumptions about the cosmos. For centuries, we have explored the heavens guided by the implicit belief that the universe is largely inert. We have presumed that the objects we find drifting through the vast emptiness between stars are dead, frozen, and harmless relics of cosmic chemistry. 3i, Atlas, suggests that this may not be the whole story, forcing us to confront a universe that might be more active and more unpredictable than we ever imagined. We often imagine that the dangers posed by the cosmos are purely physical ones, threats of kinetic force that can be overcome with sufficient warning and technological might. Yet, the story of 3 Atlas introduces a far more complex and unsettling possibility. It hints that not everything in the void is inert, that some objects may be deliberately arranged, perhaps even loaded by an intelligence we have yet to contemplate. This idea forces us to reconsider our place in a universe that might not be as passive as we assumed. Consequently, the most critical decisions of our future may not involve choosing how to act against a perceived threat. Instead, the true test could be recognizing, under immense pressure, that restraint is the only action that ensures our survival. It is possible we have just found something that we cannot safely interact with, having offered this single, profound lesson. The cosmos owes us nothing more. The object known as 3 Atlas is departing, and with it, our brief window of observation is drawing to a close. One day, perhaps years from now, a new light will appear on a screen in a quiet control room. An unknown object will trace its path across the stars, and the responsibility for what happens next will fall to whoever is there to witness it. It is my deepest hope that they will recall the lesson of 3 Atlas, that the simplest, most direct response is often the most perilous. May they possess the patience, the wisdom, and the institutional fortitude to let the object continue on its way, if that is what the moment requires. Because the alternative to such wisdom is an unimaginable catastrophe, a flash of light brighter than the sun, lasting just 1/100th of a second, followed by a silence that endures for all time.